Hi, this is Professor Jem A. Chan at California State University, Long Beach. In this video lesson today, we're going to look at exponential functions and its properties. The exponential function with base a is defined by f of x equals a to the x, where we assume that the base a is not equal to 1 and it's greater than 0. The reason why we assume that the base is not equal to 1 is because if it's the case, then we get the function 1 raised to the x, where as we're varying the value of x, we simply just get 1 back each time. And in this situation, it's not called exponential function, it's called a constant function, and that is a horizontal line. We also need to assume that the base a is greater than 0, meaning it's a positive number, because if it is equal to a negative number, then for example, if we have f of x equals negative 2, the entire quantity raised to the x power, and as we're changing the value for x, then we're getting the oscillating function values. For example, if x is equal to 1, I get negative 2. If x is 2, I get 4. If x is 3, I get negative 8. If x is equal to 4, I get a positive 16. And in this case, this is not a smooth curve, or the function values do not generate a smooth curve. Hence, it can be an exponential function. Lastly, the base a cannot be equal to 0, because if it's equal to 0, then 0 raised to the anything is 0. So then we're not really getting anything other than the point 0. Here I want to take a moment to contrast this exponential function with another function that you're familiar with, and that's called the power function. So in the power function case, we have usually a variable raised to a constant power, a. This is typically known as the polynomial function. For example, we can have x squared, x cubed, x to the fourth. So what is really varying is the base, not the power. In contrast to the exponential function, what's really varying is actually the power, not the base. At this point, you might be wondering when we actually use exponential function in real life. So I can give you an example here. Suppose that we use the function f of x equals 2x to model the number of panels we get when we fold a piece of paper consecutively x times. So when x is equal to 0, the function value is 2 to the 0, which is 1. And in that case, we simply just get the original piece of paper, and that's 1 panel. When x is equal to 1, I get my function value 2 to the first, and that is equal to 2. So I actually get 2 panels, but that corresponds to folding the piece of paper 1 time. So you actually fold right there in the middle. You get 2 panels, a 1 over here and 1 over there. When x is equal to 2, my function value is 2 squared, which is 4, and that corresponds to folding the piece of paper 2 times. In the previous step, we already have 2 panels after a single fold. Now if you actually fold it down along the vertical, you get 4 panels. And that is reflected by this number 4 here. We get 1, 2, 3, 4 panels. When x is equal to 3, the function value is 2 cubed, and that is equal to 8. So now if you take your 4 panels from before and just fold it down one more time along either direction, before we had 4 panels, and I just fold it down one more time. But now because papers are folded, when you fold it one more time, you actually created 2 creases like this. Altogether, you get 8 panels. And of course, we can use exponential functions to model a lot of other real-world situations. Next, let's try to familiarize ourselves with what the exponential functions look like. Here I'm going to graph 3 exponential functions in a single plot, and the purpose of this exercise is to develop some sort of intuition about how the graph changes as we change the base, a. Notice that in this first function, f of x, I have base equals 2, in the second function, g of x, base is 3, and the third function, h, the base is 1/2. In particular, I want you to observe the difference between graph f and g, and also again, between f and h. When we graph exponential functions, we typically start by picking points around 0 and in both directions. So I'm going to start with point 0 and then go 1, 2, 3, and as well as go in the other direction with -1, -2, and -3. Here I'm going to do a few, and then I want you to fill in the rest of the table on your own. So when x is equal to 0, for example, then f is going to be 2 to the 0, which gives you 1, because any real number raised to the 0th power is 1. And same thing for g, 3 raised to the 0th power is going to be 1, as well as 1/2 raised to the 0th power is also going to be equal to 1. When x is equal to 1, for example, then my f function is going to have 2 to the first power, and that's equal to 2. My g function is going to be 3 raised to the first, and that's 3. And my h function is going to be 1/2 raised to the first, and that is equal to 1/2. I'm going to do the negative 1 here for you. And then 2 raised to the negative 1, and that is equal to 1 over 2 to the first, and that is equal to 0.5. And 3 raised to the negative 1 is 1 over 3, and that is equal to 0.333 or so. Think of it as 0.33 here. And then 1/2 raised to the negative 1, well, we can think of 1/2 is already 2 raised to the negative 1. So when I take this entire expression and raise to the negative 1 power again, using the rule of the exponential function, I can multiply those two numbers, and that becomes a positive 1. So I actually just get 2. Alright, so please take a moment and fill in the rest of the tables yourself. Now take a moment and check your answers to see if you actually got correct values here. The next slide, we're going to plot all three functions on the same grid. Alright, in this picture here, I'm going to assume each box is of unit 1. So this is going to be a 5 and a 10, and this is going to be a negative 5 and negative 10, and so on. And go ahead and label carefully each of those points on your grid, starting with the function f of x. It goes through the points 0, 1, 1, 2, 2, 4, 3, 8. Also in the other direction, negative 1, 1/2, negative 2, 1/4, negative 3, 1/8. We keep going in the negative directions, the values are going to get so close to 0, eventually it's going to become hard to draw. I think it's safe now that we connect all those points to form a graph for f of x. Go ahead and do the same for g of x. And this is the picture I got. And from looking at it, I can see that g of x goes to infinity a lot faster and earlier than the f of x. Because, for example, when x is equal to 2, f has function value of 4, but g has function value of 9. So g is getting bigger a lot faster and earlier than f. Now go ahead and graph the function h of x on the same grid. And this is the picture I got. And by looking at it, h of x looks almost the same as f of x, except it's reflected about the y-axis. Now we've got those three graphs on the same grid. Let's ask ourselves the question, what happens to the graph if we change the base? For example, if you take function f of x and compare that to the function g and h, which has different base as the original f, what happened? What did you notice? Well, there are two things to notice here. When the base is greater than 1, the bigger the base, the faster the function grows to infinity. And this is also why we use the term exponential growth in a lot of situations, because the function goes to infinity so fast, much faster than a power function or a polynomial function. This term of exponential growth is used to indicate a rapid growth. On the other hand, if the base is less than 1 and greater than 0, then we notice that the function f of x equals a to the x can be realized as 1 over a raised to the negative x. For example, I can think of 1/2 raised to the x power as 2 to the negative 1 and then raised to x, which then can be thought of as 2 raised to the negative x. So the a here is 1/2. So in this case, the a is 1/2. If you know very well of the graph 2 to the x, then this function 2 to the negative x is simply putting a negative sign in front of the x variable. From what we've learned before about graph transformations, we know this is exactly obtained by reflecting the original function 2 to the x about the y-axis. This is why when we compare the graph of f of x and h of x, they look like the mirror images of each other around the y-axis. Next, let's look at a few variations of the exponential functions. The first example is the function f of x equals e to the x. Now this e is not the letter e, rather it's the number e, and that is called a natural exponential function. There's some very interesting facts about this number e. Now this number e is a number to which the expression 1 plus 1 over n, the entire quantity raised to the nth power, approaches as n goes to infinity. Well, and you wonder, why is this expression so important? Well, it turns out that this expression shows up in calculating continuous compounded interest. As long as you have money in an interest-bearing account, this is an expression that you most likely will care about. Okay, fine, so this e is a number that this expression approaches to as n goes to infinity, but exactly what is equal to? Let's look at a few examples here. Now, if n is equal to 100, for example, then this expression will be 1 plus 1 over 100, or the whole thing raised to the 100th power. And if you have a calculator that is powerful enough, this calculation would then become 2.70481. And try another n value big enough, let's say 10,000. An expression 1 plus 1 over 10,000, whole thing raised to the power 10,000. Again, you got to use a calculator that is powerful enough to do this, and that would be about 2.71815 ... The root expression keeps going and it's not terminating. Eventually, if you have enough time and the energy or the interest, you could plug in a number large enough, so big that it's simulating the infinity. And this number e, you'll see that it's approximately 2.7182818, and just continues going. And just like pi, this thing is not terminating. And another very rather interesting fact about this number e is that if you were to draw a graph of a 1 over x, for mark the point 1, you start pouring paint into this region to the right of 1, and if you have a gallon of paint in your hand, just keep pouring. Eventually, the point where you run out of the paint will be exactly marked at the point E. So this shaded region is equivalent to exactly 1 unit of paint. If you continue on taking calculus, then you will actually calculate this expression exactly when you use the integration technique. But that is to be anticipated later. In terms of its graph, since the number e is between 2 and 3, we would expect the graph of e to the x be nestled in between the graph of y equals 2 to the x and y equals 3 to the x. So if we go back to this graph from before, f of x here has base 2, g of x here has base 3, we would expect the graph of e to the x right in between those two, so something like right here. And remember, it needs to go through the point 1 on the y value as well, because every exponential function goes through that point 0, 1. Of course, there are also variations of the exponential functions by applying transformations to them. Let's look at a few examples next. Now here, let's think about what you would do to the graph f of x equals 2 to the x in order to obtain g of x, which is 5 plus 2 to the x, and to obtain h of x, which is 2 to the x plus 4. To get g, I would have to add 5 to the entire function value, which is equivalent to translating or shifting the entire function up by 5 units. To get h, there are a couple ways to see this. First of all, I can see it as replacing the entire input of x by x plus 4. That is equivalent to translating the entire function of f of x to the left by 4 units. This expression is the same as doing f of x plus 4. Or, alternatively, I can think of this expression as 2 to the x times 2 to the 4, by the rule of exponential function, and then think of this as 16 times 2 to the x. If you multiply the entire function of 2 to the x by 16 in the front, that's equivalent to stretching it vertically by a factor of 16. Now to graph, for part A, if we think of the f of x equals 2 to the x function in the background, and we just basically take every single y value and shift it up by 5 units. So this first point here at 0, 1, shift that up by 5 units, becomes 0, 6. The second point 1, 2, shift that up by 2 units, becomes 1, 7. And the third point here at 2, 4, with the 5 units up, becomes 2, 9. Eventually we get this new graph of g, which is 5 plus 2 to the x. Horizontal asymptote also gets shifted up as well. Before, for 2 to the x, the horizontal asymptote was at the x-axis, which is y equal to 0 line. Now it gets shifted up by 5 units, becomes the line y equals 5. Part B, you can think of it both ways. Here I'm going to think of it as stretching by a factor of 16. Again, I start with the function f of x in the background, and then just multiply every single y value by a factor of 16. If I take the value 1 here, multiply by 16, I would then reach the point 16. Take the second point, 1, 2, multiply that by 16, it gives me 32. Pretty fast, it's already out of the grid that I can graph. So I'm going to just assume that if I get a point here, is equivalent to 32. This graph here is a lot more drastic in terms of its values than the original function f there. If you focus on just this portion of the function f and h, you notice that the blue graph does look like a translation of the f function left by 4 units. Functions are often used to model population over time, such in a model that's called a logistic model. So in the next example, such an example to show you how it could be used in real life. Disease begins to spread in a small city of population 10,000. The number of people who have succumbed to the virus is modeled by the function v of t is equal to 10,000 divided by 5 plus 1245 times e to the negative 0.97t. Model, then it will look something like this. And the fact that it actually kind of plateaus in the long run is indication of a logistic model. If you are most interested in general, first, for example, how many people were infected initially? Will be infected after a period of time. And also interested in knowing how many people would eventually be infected by this virus. First question, how many people were infected initially? Since the t-value represents the number of days after its first infection, we would then equals to 0 to figure out how many people were infected initially. That is to find the value v of 0. Equal to 0 in my expression, I get 10,000 on top, divided by 5 plus 1245 times e raised to the negative 0.0. But any number is a 0, which makes the entire exponent equal to 0. But then you take e raised to the 0th power, which gives you this entire expression 1. And this written down to 10,000 divided by 5 plus 1245. And we know that 5 plus 1245 is 1250, so this really reduces down to 10,000 divided by 1250, and that is equal to 8. And remember to use the correct units for the problem. It's asking for people, and so we can answer this question by saying that 8 people will have the disease initially. How many people will be infected after 1 week? In 2 weeks. Round the answer to the nearest digit because we're dealing with people here. Since t is measured in days, we have to make sure we change to the appropriate value when we evaluate the function. So 1 week is equal to 7 days. So the first thing we're going to calculate is v of 7. And that is when we get t equal to 7 into our function expression. So I get 10,000 divided by 5 times 1245 times e raised to the negative 0.97 times 7. To figure out how to use your calculator correctly to evaluate this expression. If you do it correctly, you would get something like 1562.4, but remember we're rounding it to the nearest digit, so I would say this is 1562 people. I would change the t-value to 14 because that's 14 days. Response is 1999.4 people, and that gets rounded to 1999. Continue asking these questions. How many people will be infected after 3 weeks, 4 weeks, a month, 3 weeks? Ask the following question. How many people will eventually be infected by this virus? In other words, what is the end behavior of the function v as t goes to infinity? The word eventually is indicating that we're looking for a long-term behavior, and a long-term behavior is synonymous to an end behavior. So then as t goes to infinity, what happens to our entire function v? Well, let's investigate that in pieces. Let's start with e to the negative 0.97t expression. As t goes to this expression is equivalent to 1 over e to the positive 0.97t. It's easier to actually evaluate this expression. Again, when t goes to infinity, this entire expression goes to infinity. And then we have e raised to a very large number. This entire expression then goes to infinity as well. But because it's in denominator of a rational expression, we actually have 1 over a very large number. But that is equivalent to saying it goes to 0. The entire function v of t by exponential portion of it goes to 0. Then we have 10,000 over 5 times 1245 e to the negative 0.97t. This portion of exponential function goes to 0 as t goes to infinity. So then I have entire function goes to 10,000 divided by 5 plus 0 to 10,000 divided by 5, and that is equal to 2,000. So in other words, behavior, or eventually the number of people who are going to be infected by this virus is going to be 2,000 people. And you can kind of see that has to be the case from our previous calculation there. When we calculated the number of people infected by 2 weeks, it was 1999, which is very close to 2,000 already. Message given here. The fact that the amount of people infected by the disease eventually stabilized is likely due to vaccines, treatments, or preventive cares, etc. This type of model is called logistic model. And ask, which involves another type of mathematics, is after how long will a number of people be infected? So for example, 1,000 people. Well, in this case, we need to find the value t such that v of t is equal to 1,000. So we get 10,000 equals 10,000 divided by 5 plus 1245 times e to the negative 0.97 t. To solve this, I can think of the 1,000 as 1,000 over 1. So you have a fraction equals a fraction. So we can do this cross multiplication trick. This 10,000, which is 10,000, equals 1,000 times 5 plus 1245 times e to the negative 0.97t. 1,000, then the right hand side goes away, and the left hand side is reduced now to 10. Back 5 both sides to obtain 5 equals 1245 times e to the negative 0.97t. But I don't really like to deal with the negative exponent there, so I'm going to change this to a positive exponent by writing it as the equivalent expression 1245 divided by e to the positive 0.97t. And then I realized the 5 on the left hand side is a fraction of 5 over 1 as well, and then do this cross multiplication trick by multiplying a 5 with e.97t and then equals to 1 times 1245. So I get the overall expression 97t is equal to 1245. Next, I divided by 5 both sides to isolate the exponential function completely. I would then to the 0.97t is equal to 249. Now this is as far as you can go at this point without using any other mathematics. This question, what we really want to do is uncover this t-value or isolate that t-value all by itself. So what I need to do is to undo the exponential process, because that's where t is right now, is at the input function of the exponential function. So to undo the exponential function, I gotta use its inverse, which is the logarithmic function, which you'll learn in a separate video. But at this point, you can leave it as it is, or if you actually are familiar with the logarithmic function, let's continue doing this. We apply the inverse function of the exponential function, in particular, and that is going to be called the natural log. So if I do natural log e to the 0.97t is equal to the natural log of 249, and that is applying natural log both sides, then I would be able to cancel the natural log and the e because they're opposite functions of each other, and that's why they're called inverses. Then I'm on 0.97t on the left, and then the natural log of 249 on the right. One more step to isolate t is by dividing at 0.97 both sides. So t is equal to the natural log of 249 divided by 0.97. And that is approximately 5.69. And remember, that is in terms of days. So I would say that in about 5.96 days, the number of people infected is going to be 1,000.